Okay, guys, we got to rock and roll on Unit 2 now. Unit 2 is about reasoning and logic or proof. And that's a big basis in math, is how do we know that mathematical claims that we're making are true? Since math builds step by step upon itself, then we need these kinds of reasoning rules in order to make sure that the claims that we're making are really true. And so that's what this whole unit is about. How does math use reasoning and logic to make the claims it makes? So the first type of reasoning we're going to look at in this unit is called inductive reasoning. And we got an example here. Let's say that this gal has been out on 5 different dates during the summer with 5 different guys. And every time she's gone out, those guys have been at least 15 minutes late to pick her up. So it's homecoming and she's going out with a new boy and she's running a little late herself, but she doesn't worry about it too much because since all her other dates have been at least 15 minutes late, she's figuring she's got at least 15 minutes because he's going to be late. And that's an example of inductive reasoning. So she has made a conclusion based on some past experience or based on some different examples, these different boys, and drawn a conclusion based on that. So what is inductive reasoning? Inductive reasoning is the process of using careful observation to look at several examples, and by several we mean more than just one or more than two. We're looking at least 3, and the more the better. So careful observation of several examples to find a pattern. And when you find a pattern in those, then you make what's called a conjecture or a conclusion, a claim that you're going to make about that pattern. So let's give it a try with this sequence. We've got 3 terms in a sequence, 3, 6, and 12, and what's the pattern we want to look for? If we look at that, we can see that 3 times 2 is 6, and 6 times 2 is 12. So maybe that's the pattern. Maybe we're just multiplying by 2 each time, or doubling it. And if that's the case, then our next digits would be the 24, 48, and 96. Or if we look at this pattern, what would be the next 3 terms of this sequence? Doesn't look like things are being doubled. How do we go from 7 to 8? Well, that would just be adding 1. And then from 8 to 11, if we're going to add again, that's adding 3. So 1 and 3 are odd numbers. Maybe we're just adding the odd numbers. So we might say, well, let's add 5. What would be next? Then 16. The next odd number would be 7. Add that to 16, and that's 23. Then add the next odd number, which would be 9. And we could keep continuing this pattern. So maybe that's the next 3 terms of the sequence. So we observed, we looked for the pattern from looking at several examples, and that's what inductive reasoning is involved. So once we're pretty sure that we see a pattern, we make claims about that pattern. And that claim that we make is called the conjecture. It's the conclusion that we're reaching based on the pattern and based on our inductive reasoning. Okay, so let's make a conjecture about this next pattern. Let's see if we can see what's going on here. We want to know what number of circles would be in the 30th picture. Now, I don't know about you, but I do not want to draw 30 of these pictures to figure that out. So we're going to try to make a conjecture based on the pattern that we see. So we've got 1 circle, 4 circles, 9, and then 16. And this is the first 4 pictures. Now on this one, I'm noticing that all of these figures are making squares. So maybe we could look at it in terms of how big the square is. If we look at our last one, that's 4 circles wide, and it's 4 circles long, and so we have a 4 by 4 square. That's where we're getting the 16 from. Over here we had 3 by 3, and this was 2 by 2 and 1 by 1. So maybe it's going 1, 2, 3, 4. So how many would be in the 30th picture? Well, I'm going to conjecture that widthwise it would be 30, and lengthwise it would be 30 also. So I would guess that circles, all filling this up on all those directions, would be just like these others, just to take 30 by 30, 30 times 30, or 30 squared. And that's going to be 9,000. So my conjecture is that there would be 9,000 circles in the 30th picture. So the inductive reasoning that we did here was to look at several examples, look at them closely, see what kind of a pattern we could see, and then extend that pattern out to the 30th example. Sometimes a conjecture is called an educated guess, and based on those observable patterns. But unfortunately, not all of our conjectures are going to be right. We might miss something in the pattern or think we see something that we really don't see. So if we want to show that a conjecture is actually wrong or false, then we need to find one example that would show that it's false. And that example is called a counterexample. So let's take a look at how counterexample works to prove something false. In this example that claims that if the name of a month starts with the letter J, then it's a summer month, like June or July. Was that always true? Well, a counterexample in this case would be the month of January. Since it starts with a J, but it's not a summer month, that proves that statement is false. Now this conjecture says that if a number is divisible by 2, it's also divisible by 4. Is that true? Well, if we think of some numbers divisible by 2 like 12 and 8 and 10, each one, 2 goes evenly into those, but does 4 go evenly into those? Well, 4 definitely goes into 12, and it goes into 8, but when we look at the 10, we see that 4 doesn't go evenly into 10, therefore it's not divisible by 4. And so this is a counterexample. It shows that the statement is false. Okay, this next set of questions is all for you to try on your own, and we'll discuss them in class.